Dudzik from Google DeepMind, who will tell us about tensor species. So please, Andrew, take it away.
Sure, thank you so much. Sorry, we couldn't figure out how to hide the UI elements here in time. So I'm honored and a bit intimidated to be asked to speak here at this colloquium. I'm kind of here attempting to bridge two worlds of people, making stuff but not really understanding what they're doing, and people understanding stuff but not really making anything with it. So I'm gonna kind of try to deal with that in a good way. I think maybe a lot of what I'll say won't be so understandable to anybody from the machine learning community coming to this later on YouTube, but I will do my best. So basically, I'm here representing a community at DeepMind that has been doing a few papers for a few years, and we're focused around kind of the theory of what code is actually going into neural networks. Like, what are we actually doing concretely when we are writing and kind of architecting new things? And we have this shared belief that we can actually innovate in architectures using sort of an abstract understanding of code structure. And we believe this even though there is a lot of empirical evidence to the contrary. There are a few reasons for this that I'll kind of get into, but we're sort of still trying to understand some of the basics. So as I see it, like, there's a few things that go wrong, and these are some of the big ones I could think of. In the first place, a lot of theory is sort of aiming at the wrong place. Like, there's a lot of interesting mathematics to be done, but sometimes a lot of it's being done in some area where people who are more on the engineering side are, they sort of already know there's nothing there, or already know that it doesn't concern them as much, and sort of innovating in those ideas may not be as directly profitable. And then there's sort of deeper reasons. Classical programming and sort of programming in neural networks are different enough that if you're basing your understanding too much on kind of what's been written about high-level programming languages and so on, you can end up kind of missing some crucial features of the kind of neural side of things. And in particular, it may be that someday we have high-level programming languages for writing neural network architectures, but at the moment, the code that we write is extremely close to the machine level. Not quite directly always dealing sort of explicitly with memory and buses and things like this, but you really are kind of always dealing with concrete representations of things in memory. And that's rarely the case in the way high-level languages are treated. And then the last thing is, like, there's sort of different features in distributed computing. And both the training and execution of neural networks are distributed in different ways. In the first place, the actual hardware that it's run on is sort of, has like hundreds or thousands of sort of small cores that are doing low-level work, and then additionally are often sort of spreading things across many computers, potentially millions of them. And you sort of can't really think about this without kind of immediately thinking about things like how fast are my cables, what kind of data can be communicated from here to here, and so on. So there's sort of are a lot of details that become very relevant when you start to think about neural networks in a practical setting that are often not there in the kind of abstract formulation, or not easy to interface with. And I'm going to be kind here, and as an example of things not working, I'm going to use one of my own papers. This was with Bruna Gavranovic and Paul Lessard. This paper, we smuggled a category theory paper into a machine learning conference as a position paper. And the sort of core idea here was to take the classical view of monadic programming and so on, and kind of lift this up to the two category of sort of parametric maps.
So Andrew, I'm sorry to interrupt. Are your slides advancing on your side?
Yes, they are.
Okay. We are still seeing the title slide. Oh, there we go. Okay, something just happened for the first time. So I'm not sure what you did that's different, but
okay, sorry. I yeah, thought this was debugged, but no, I just went out of full screen mode. So I'm just going to stay
okay.
out of full screen
So I
mode.
guess that's what you'll have to do, is stay in this other mode. Thanks. Yep.
All right. Yeah, not used to presenting on Zoom. Okay, so I had this slide. This was the bullets that I went over about kind of issues with theory. So right, so we wrote this paper, and the idea was to lift up sort of older viewpoints on monadic programming and so on into kind of two monads, and therefore have a general way of looking at programs where you have learnable parameters attached. And this kind of seems like a nice thing to do, and it leads to a clean picture. But it kind of doesn't give you new architectures very easily. And sort of, oh yeah, here's the sort of pictures of the different algebraic and co-algebraic kind of structures that we looked at. But like, here's a kind of breakdown of why this sort of thing is problematic. So when I'm storing discrete data types, sort of in the classical setting, like, we often take it for granted that we can form product types. But the issue here is that in neural networks, we have vectorized data. And very often, the interpretation of these vectors, it should be kind of distributions on a finite set. And sometimes they're literally probability distributions. And if I want to compute now a probability distribution on the product, I really need to be taking the tensor product of my vector spaces, right? And it's no longer the case that I can form, say, higher powers of data types cheaply, right? In fact, sort of, second powers are expensive, and third powers may be prohibitively expensive, and so on. And so we sort of rapidly run into assumptions here about like what sorts of programs are going to be interesting and where do we need to be paying attention. And a lot of this kind of analysis doesn't naturally fall out of just taking those views and kind of transposing them into a setting where learning is taking place, right? We really need to be thinking about vectorization. And one way I sometimes think about this is that neural networks are really, I feel like they're really closer to being quantum computers than they are to being classical computers, because you sort of have vectorization and like, kind of entanglement and all of these things. But the real issue with sort of a lot of what's been written about the structure of neural networks is that it tends to ignore attention. And attention is something that I think every year there's more appreciation. Finally, I think I just have to say attention, and everybody will know that that's something important. But it's been a long time getting here. Sort of the professional community has known about attention since 2017. I think it was kind of exploding in 2019. I couldn't find an earlier use of the technique than neural Turing machines in 2014. But in any case, I think it's slowly taken over sort of various neural network architectures, and it's become kind of the main thing that you do. And I got into a habit for a few years of every time I would watch a talk on sort of the theory of neural networks and architectures, I would ask kind of what does attention look like in this framework? And the answer was basically always the same, which is I haven't thought about it yet. The idea being that somehow it's just a special case of some general view. And I'm going to sort of argue that it's really, there's something interesting going on. And I'd argue we haven't really properly understood, kind of in an algebraic sense, what's going on in attention. And yet, this is a surprising fact because the actual code is not complicated. And I'm going to point here to a paper by Noam Shazir, one of the sort of grandfathers or godfathers of attention. And his sort of example code is incredibly simple. And we can kind of see here just really 3 lines of code. One of them is this thing called an Einsum, which I will discuss in more and more detail. And this is some kind of shape-changing operation on tensors. And then there's this softmax, which I'm also going to talk about later into the talk. And then another Einsum. So this is, there doesn't seem to be much happening here. So it's a surprising thing that there seems to be some work that's not done. And now this is the simplest possible way you can write down attention. Not usually how it's done in practice. Usually we use more complicated things, but even those more complicated things, say multi-head attention, still follow the same basic paradigm. You can sort of see there's a bit more going on in terms of the inputs and shapes and so on. But we're still basically sandwiching a softmax inside of 2 Einsums. Okay, so before I get into sort of talking about Einsum, I'm going to talk a bit about how I got involved in this and kind of what actual concrete things we were trying to do when all of this mess came up. And the sort of scene setting here is that everything we always thought computers were good at, neural networks are extremely bad at as a rule. And the term I want to really emphasize here is length generalization, which is in a sense the most fundamental kind of generalization that we don't know how to deal with. Good neural networks are trained on a data set, but hopefully that data set is rich enough that they generalize to examples that were not in the data set, right? But this is difficult to do when dealing with problems where the inputs have variable length. If I can certainly learn to add 6-digit numbers, but then what about 7? You've never seen 7. And the point is that no matter how good my data set is, I'm always going to have some limit to the size of n that the network has been trained on. And this is kind of a big problem. And to see how big of a problem it is, there was a lovely paper last year from Federico Barbero, who was a student researcher here. And it sort of explores all the very basic things that LLMs seemingly can't do and provides some nice kind of heuristic justification for why this is a kind of structural limitation, which is to say, it's not because the data wasn't good enough. The network itself is struggling to kind of find the right representation. And these graphs will give you a sense of how bad this is. So these blue bars, these are error bars, okay? So in other words, if we're asking a transformer to count 50 things, it's already starting to run into trouble, right? And by 100, it's starting to make a lot of mistakes, and it's sort of totally unreliable, for anything actually big. So this is really bad, right? We would hope that that you could count to 1 million or something like that. But it's really not working in our most widely used models. And there was also a very recent paper that gave some hint as to what are they trying to do. Like when transformers are trying to count, what are they actually doing? And there's evidence that they're sort of making use of kind of rotating helixes and so on, which is pretty interesting that there's kind of that much structure to what they're doing. But it also should be clear that a helix might be a good way to represent, a couple of digits, but it's not a good way to represent really large numbers, right? You really want some kind of multi-digit representation and so on. So they're learning something. They're learning some structure, but in a sense, the length generalization part, they're really not able to learn at all. And I started thinking about this as a result of working with Petr Veličković, who kind of spearheaded this nice open source project called CLRS. And those are the initials of the authors of a well-used algorithms textbook. And they kind of used graphs as a common language, and they basically put 30 algorithms in the form of tasks for a neural network to learn and to be tested on. And here are some kind of pictures of various algorithms. So sort of sorting, shortest path finding, various problems of that nature. Scheduling, string matching. So the point was, benchmarks are always a really fundamental thing in machine learning because people don't understand what they're doing, but they understand when the numbers go up. So as soon as you make a benchmark, there's a kind of competition afoot. And this was sort of a nice way to make sure, like here we have standardized inputs, standardized outputs. Can neural networks learn to behave like these classical algorithms? And, again, keeping length generalization in mind, the point here is that depending on what sort of architecture you use, generalization can be great or terrible. One of the most common questions I get about this benchmark is, can't you just use a transformer and solve it immediately? And the answer is definitely not. It will easily learn whatever training data you give it, but then when you present it with larger n, so if you train it on graphs with 32 nodes and then give it a graph with 64 nodes, things will just fundamentally go wrong. The beginning of the attempt to think about what networks are good and what networks are bad at this kind of thing started in 2019. And this was a paper of Xu. And the idea was pretty simple. And depending on how you say this, it's either very profound or very trivial, which is that somehow networks are good at learning algorithms if they share execution structure with the algorithms that they're trying to learn. The trivial version of that is you can pretty much write the algorithm into the neural net, and that's obviously going to work. But the deeper sort of question here is exactly what do we mean by execution structure? Like, what are the mathematical elements present in both the architecture and in the algorithm? Which elements do you need in the network? Because the sort of holy grail here would be if we found some component which could perform a function that sort of is lacking in transformers and then somehow transplant them into the transformer. That might be too much to ask for various reasons, but that's the sort of dream. So identifying these components is a really kind of basic thing that we want to be able to do. And this is what led to the first paper I wrote with Peter, which tried to look at some of this execution structure and get to the bottom of what was going on. So here is where I think I might get some people's attention, which is that we found that these strange looking diagrams were a really useful way of capturing the way that shapes were being transformed in graph neural networks, and that these lined up exceptionally well with certain classical algorithms of interest. So somehow this diagram where these are finite sets, x, y, w, and z, this diagram somehow captured something important about what operations were occurring in each program, right? And we connected these with something that we called it the integral transform. And the idea is if R is a commutative semiring, then you can use one of these diagrams as a set of instructions for how to transform things of shape W, so tensors indexed by W, into something of tensors indexed by Z, right? And this is somehow not super complicated, but right, you pull back or re-index in the left map, and then you do a fiber-wise multiplication, and then you do a fiber-wise addition. Now, this is somehow very simple, but it's a funny story that we stumped more than one category theorist with this, because this obviously resembles polynomial functors, and yet it's too vulgar to be polynomial functors. Like the multiplication is not right adjoint to the pullback and things like this. So this was a good example of category theory making things more complicated, because we ended up kind of needing to say this in order to justify this. You know, that this category of polynomial diagrams is actually the Levier theory for commutative semirings. This is in Gambino and Koch, and I think it's attributed to Tambara, although I couldn't find it in Tambara. But basically, if I have a monoidal functor, then the image of one kind of picks out my semiring object in my target category. But I just find it funny how much work it took to basically justify saying, look, these are polynomials in natural numbers, so I can plug real numbers into them, or something like this. But in any case, something interesting did come out of this, and that was, you know, we already kind of had this alignment of the diagrams, but there's still a missing piece, which is which commutative semiring do you use in the computation? And somehow lining up the semiring operations turns out to be the single most powerful thing you can do to improve length generalization. And this is interesting because somehow people writing neural networks are always using Euclidean operations just from muscle memory, just because, you know, everything was based on linear algebra and matrix multiplies and so on. And yet, in the classical setting, even when the structure of the computation is identical to what's happening in a network, it's happening in this tropical setting. It's happening where you're sort of taking a max over sums rather than taking a sum of products. And it is still true today that the most performative networks on the algorithmic benchmarks are relying on this trick where you sub out the ordinary operations, the Euclidean ones, for tropical ones, are kind of smooth approximations of tropical operations. But it's also, you might also ask, well, do you really have to pick this structure? And there's been some work on this. Yuan Ong did a follow-up paper of particularly interested in the addition, like all the different aggregators that you can learn, like there are sort of top K aggregators and various things. Can you actually have the aggregation performed by a little neural network that learns which commutative monoid it should be using? Right. So this was something interesting to kind of come out of this perspective, right? You've got these diagrams, and then you've also got the underlying algebraic structure that needs to somehow match up. And now I'm going to finally explain what an Einsum is, if there's no questions so far. I can't see the screen, so. Okay, so Einsums are, the name is based on Einstein summation, although it's annoyingly not exactly the same as Einstein summation, but hopefully I can convey to you what it is here. So the idea is that I somehow want to, in as little information as possible, convey some operation on tensors in a way that there's no ambiguity with what sort of happens to the indices. So, for example, this first one, which represents the trace of a matrix, the input is indexed II, and the output has no indices. So we're supposed to read that as, okay, the input is an n by n matrix, and I sum up over the diagonal. I have to sum over I because I doesn't appear in the answer, right? And then likewise, if I do put I in the answer, then it's the same thing. I do the same diagonal indexing, but I don't sum. And then I can also perform outer product this way. I can perform various sums this way. I can perform the matrix transpose, and then kind of the interesting one here is matrix multiplication, and then a lot of sort of higher analogs of matrix multiplication where you can sum over various indices. And this basically is the fundamental operation for changing shapes inside of a neural network. So we're dealing with this sort of multidimensional rectangular data, and one of the most basic things you want to do is reshape and combine stuff and so on. And it's good to think in terms of Einsums, because just almost everything you want to do that's not too super highly optimized is going to be phrasable in terms of these sorts of operations. And the sort of thing that we realized sort of after this paper is that polynomials are a nice way to write down Einsums. So again, we have the trace here on the left, kind of same information being expressed, right? We index into I times I with the diagonal, and then don't multiply anything, but then sum over I, and something similar here on the right, where our input has shapes I and J, right? So we have something of shape I, something of shape J. We kind of re-index, so both things are indexed by I and J, and then we pairwise multiply, and then finally we do nothing at the last step, right? We don't add anything. But we were clued in by a paper of Bergomi and Vertecci that this was somehow, you can express this more concisely using these multi-footed spans. They called them parametric spans because for them, the middle foot was always pointing to a set of learnable parameters. But we're in a more general setting here, so maybe parametric isn't a good word. But the convention here is that the right foot of the span points to the output. And with that convention, sort of, you end up expressing precisely the same information as were being expressed in these polynomial diagrams. Now, these have a really nice property, which I'm leaving as an exercise, which is that if I want to compute gradients through an Einsum, then it's also an Einsum. And basically, the proof here is that you can permute the feet of these things, which is very nice to know, because when you write neural network code, you want it to be efficient code, but you also want the backwards pass when you're computing gradients to be efficient. So knowing that we're using a set of operation closed under gradients is pretty nice, and one of the reasons this is such an amazingly useful class of operations. The next thing I want to talk about is, we're dealing with these diagrams, and we kept thinking in terms of finite sets I, finite sets J. But there's something kind of missing from that perspective, or at least two things. And one of them is the notion of hyperparameters. So you often see pictures of tensors like this. Generally, you see lots of magic numbers when people draw pictures of neural networks. But the fact is that the code itself is almost never contains these magic numbers directly. They're things that are fed in from outside of the program. Typically, you have well-defined behavior as these tensors vary, right? So you really want to think about pictures like this for sort of varying values of 5 and so on. What else did I want to say about that? The sort of other bit here is symmetry. So a lot of what's happening when networks are being trained or executed is sort of heavily distributed computation. And this has a kind of funny effect, which is you're always chopping up the computation and sending it to lots of different places. And so in a sense, you're always kind of thinking of these chunks as being indistinguishable chunks, if you're cutting the tensor up. And this is true even if you care about the ordering. And this is not very intuitive. So I'm going to try to explain this with sort of this diagram this is a diagram of a transformer, specifically one being used as a language model. Now, when you run a language model, you're feeding it a sequence of tokens, say T1 through T5, and then you're getting T6 out, the prediction for the next token. It's trying to guess what is the next token. And if that was all you needed, then you could sort of do fully symmetric computations here and use all of these arrows. But transformers do something a bit strange, which is they actually predict T2 and T3 and T4 and T5, etc. Or they kind of generate outputs that allow them to predict these things. Why is that? The reason is training. So at training time, you have this tremendous gain in efficiency because you can feed in a whole list of tokens. You can feed it in a whole text. And each token of the text represents a different prediction task. Predict T2 given T1, predict T3 given T1 and T2, etc. And this is one of the big reasons that transformers are just as dominant as they are in language models is this tremendous training efficiency. You run the transformer one time and get all these different predictions, which you can improve all of with a single backwards pass. And the only reason this works is that we throw away all of these interactions that would violate causality, right? We make sure that information is only flowing forward. This, as you might imagine, this leads to some very difficult debugging when you're working on transformers because you're feeding in information that allows it to cheat. So you need to design everything carefully so that it can't cheat. Now, this is very strange because like we're breaking symmetry, but we're breaking it in the most basic way possible by just cutting some connections. And in fact, the symmetry is still present sort of in the remaining connections in the sense that as written, without something extra, we don't actually, you can't tell if you get some information, you can't tell who you got it from. You can't tell if you say this word was here, you don't know where here is without something extra. So we actually need to inject information in the form of positional encodings to recover that information of where the thing came from. The computation being done is symmetric. So that information is not kind of inherent in the computation being done. Now, this works the opposite of how a lot of people think it should work. I often hear that kind of the right way to process data is to be kind of mindful of the structure of the data. So in this case, the data is a list. You might think, oh, step through the list as a list and predict as you go. And yet this absolutely is not how transformers work, and transformers are much better than stepping through like a list, which is the sort of recurrent neural network style. So like my main point here is things are symmetric even when they're not, or there are gains to be had by keeping track of symmetries, even symmetries that you think aren't present. Okay. And then the sort of final two things I wanted to mention along these lines was in the setting of graph neural networks in particular, there's been a lot of work starting with deep sets about the importance of the symmetric group and kind of making sure that when you do computations on graphs that you get the same answer even when stuff is mixed around. And then there was this other paper that really got us thinking about the functorial viewpoint here, which is graphs are a bit too complicated for us at the moment. But the point of natural graph networks, which is a really beautiful paper, was to say that a network which takes a graph as an input should behave nicely if you apply a graph isomorphism, which is to say that the input of the, you don't input a raw graph, you input a representation of the graph, but then there might be some non-trivial isomorphism with some other inputs, and you should make sure to build something that respects these, right? And they did this using functors out of the group weight of graphs. So this is all to kind of set up how it is that we got thinking about species. And I'm going to say a few things here that we thought were interesting. I don't know how many of them will be deep, but we're mainly going to be dealing with finite species here, although I actually do have a species later that's infinite. But we're dealing with finite species because computers are finite. And this is one case of making sure that everything we say has an interpretation in terms of the execution of these networks, right? As soon as you start dealing with infinite data types, there's problems. How are they represented in memory, and so on. And, so here's sort of a standard example of a species, and we're interested in these for multiple reasons, one of which is tensors, and one of which is sort of the data types, the combinatorial data types that come up when we talk about algorithms. And so we also are going to want to talk about vector species, right? And we're also going to think about multivariable species. And this gives us a slightly cleaner or more universal way to say what an Einsum is. So if I let I, j, and k be the three projection functors, now I can sort of go back and interpret these Einsums as actually polynomials in species, right? So the thing I like about this view is it's a bit more honest in terms of how the code is written, right? We don't know the size of the indexing sets when we create this operator. And we understand that it works for various indexing sets. So the point is that this diagram, again, is matrix multiplication. And it sort of, you can think of it as the instructions for how to turn a tensor of, r to the I tensor r to the j, and a tensor r to the j tensor r to the k into one of r to the I tensor r to the k. So this is like a polynomial map of tensor species, something like that, or vector species. I'm interchangeably saying tensor and vector. Usually, for machine learning people, usually a vector is something where the indexing set is sort of one-dimensional, and a tensor is anything bigger than one-dimensional. And similarly, we kind of have these trivalent spans as a kind of nice description. So there's probably even a bit more to say about shapes, but at least this is a kind of satisfying, I think, description of these objects. Maybe there's an even simpler way to look at it. And this covers quite a lot of how shapes are transformed inside of neural networks. Okay, I did want to say a few more things about species that we like, that seem interesting or that we found useful. So in the first place, I do think it's really nice to have a generating function associated to species, because sometimes I find it unclear when something in category theory is deep or trivial, and it's kind of nice to have various machines around to rapidly decategorify and check to see if something is happening. It's not a foolproof method, but it can help keep you a little bit honest, in my experience. And I think I'm obligated to say this thing about analytic functors, so that species lift up to analytic functors. And so there's this relationship with polynomial functors. I think this is certainly old news for anybody who's been going to a lot of these colloquia, but this is sort of, it's good to note that essentially taking groupoid cardinalities of this is how you get the actual generating function. Yeah, and I just want to give, with that in mind, some examples of useful species, useful for the types of things that we're thinking about, and their generating functions. And yeah, I mean, sometimes I just write the generating function instead of the species. But in any case, what do I want to say here? Right, there's a lot of graphs, I guess, is my takeaway from this. So, but the really useful thing here, and I want to emphasize that the reason for us to think in terms of species is a kind of correct by design principle, which is we want to make sure, again, that we are tracking in our data types the action of the symmetric group. But we also really want to know what happens as n gets big, right? And the nice thing is, when you have the species, you can just read off the memory footprint, right? And so again, here C is the number of bits that we need to encode the real numbers. I think probably we should think of the real numbers as a species, like a species of floating point approximations or something. But in any case, if we fix a floating point size for the reals, then we sort of can see that some things just are not ever going to be stored in memory. And this is good to note, because in the algorithmic setting, you are often generating discrete data types from vectorized ones. And in certain cases, like the first two rows here, you can comfortably say, well, I'm just going to generate a probability distribution over the possible values here and sample from it or something like that. This doesn't work, or doesn't immediately work for anything that gets too big, right? Even though I can store a total order in memory easily, I absolutely cannot store a general probability distribution over total orders, right? So anytime I'm generating a total order, I'm going to need to make some choices about how to do it, and those are going to potentially affect the result and things like that. So there's kind of something interesting needs to happen, right? If you want a neural network to output a graph. And it might be, if you're interested in this kind of thing, our paper, A Generalist Neural Algorithmic Learner, I think it's called, we talk about how we generate permutations out of a neural network. And this is some trick where you do repeated exponentiation of a matrix to get a permutation matrix, but then there's tie breaking that needs to occur, so noise needs to be injected. You need to potentially do a lot to sample these data types. And that's going to complicate right, this notion of algorithmic alignment, like the different ways you do it might be better or worse for generalization. And then the last, I wanted to mention sort of monoidal structures on species. I'm probably, yeah, I'll maybe speed up a little bit. But I just wanted to kind of, I think I remember reading in David Spivak maybe that there's 10 different monoidal structures on the category of polynomials. I think it's the same thing for species. I couldn't find all 10, but there's 2 that are interesting for us. And one is the Cauchy product, which has this sort of nice combinatorial interpretation. And you can sort of cleanly write it out sort of like this. And the nice thing here is somehow like monoids and comonoids with the Cauchy product are very relevant to some of what we think about. So a lot of the data types where you're sort of walking around in the data type, like a graph or like an ordering, have the property that they're Cauchy bimonoids. And then these have a really lovely theory. Sort of when you vectorize, they're usually hop, and there's sort of sort of nice inversion formulas. So this is sort of active work that I don't have a lot to say about, but we're very interested right now in kind of algebra and coalgebra and bimonoids and so on. And this is something that we're kind of there's something here. There's some connection between dynamic programming and kind of bialgebras that we hope to have a paper on this soonish. But anyway, the other product is the substitution product, which is sort of related to the combinatorics of partitions, right? And we have sort of this formula where we are kind of putting a structure on the sort of different sets in the partition, the set of sets in the partition, and then putting a structure on each individual set. And this corresponds to composition of generating functions. And then of course, like monoids here are operads. And I just want to mention one operad, the simplicial operad, because it's going to come up in 2 minutes. So here, we have something much more complicated than what's going on with kind of, composing vector operations and so on, where we have a nice monoidal structure, the multiplication of the reals. Here, something much more subtle happens, which is that we form joint distributions by tree-like composition, right? And this is going to be an interesting thing for us in a moment. And of course, it took us quite a bit to appreciate that monoids are just very boring operads. And that's the main thing that I'm going to say about sort of species in general. And I owe you a description of what attention is. So I'm hoping I can do that reasonably quickly here with a little storybook. So this was sort of the example. I came up with this example, and it was sort of finally how I understood attention. So I hope it's useful to you. So Nancy and Martha are two intelligent computers, but they have very limited input and output bandwidth. Okay. Nancy can input or output just a bit at a time, whereas Martha can do 3 bits at a time. So Nancy has been thinking for a long time about a problem, maybe generating bits and feeding them back into herself or something like that, but she's stuck. She has a question, and she needs an expert to answer this question. And it turns out that Martha is an expert. So she decides to ask Martha. So how does this communication work? Well, first, Nancy generates some bits. Boop, 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 boop. And we call this the query. So this is the question Nancy is asking Martha. And now Martha sort of knows the format of the question and knows 3 possible answers that she might give. So she generates those. Boop, boop, boop. And those are stored off to the side as the possible values for this computation. And then in order to figure out which one to return, she has to sort of generate keys to match against Nancy's query. So she does that. Boop, 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 boop. And now we can see that there's 2 reasonably good matches that match in 3 places. The last one only matches in 2 places. So there's this matching that happens. And then based on the match, some of the values are selected out. And then there's one more slightly tricky bit, which is which one do we send? What's our strategy for actually sending a result? And there's kind of 3 different things that we can do here, which is we can do some form of tie breaking, or we can kind of pick something randomly. But the standard way to do this in a neural network is you take the expected value over a probability distribution. So you basically sum up the answers according to how probable you think they are. So you send a kind of superimposed answer, right? Here's what's going on in shapes. So the key thing to note here is that somehow the attention mechanism is sort of a conjugation of the selection function. The selection function does not change the shape, right? But we start with an n by k shape, and we kind of transpose it into this other shape. We apply the selection, and then we kind of transpose it back. More or less. That's, I think, how we should think about it. How do we actually do this selection? The textbook way is the softmax distribution. And this is just you exponentiate to make sure everything is non-negative, and then you normalize to make sure everything sums to 1. We generally scale by a factor of beta. And this means that actually this is sort of exactly the Boltzmann distribution, although the sign is not quite right. I suggest thinking of the L sub I as negative energy, because otherwise a whole generation of machine learning scientists have been calling temperature negative temperature and so on. So for their sake, just think of the L sub I as negative energy. And as beta goes to infinity, we kind of pick out just the maximum. And I say almost because if there's multiple maxima, then we actually get the uniform distribution over all of them. So again, there's this kind of tie-breaking problem in the extreme. So this is an interesting thing because, we have this nice thing that is used everywhere, but it also can be used to approximate these kind of tropical things that I mentioned before. These sort of these common discrete operations, again, with the asterisk about tie-breaking. Okay. I guess I've got a couple more minutes to say a few interesting things. The key point here is that almost always you're going to see masks with softmax. As I said before, we have the causal mask in large language models. We sort of replace logits with negative infinity to send the probability to 0. But we can't replace all the logits with negative infinity. So softmax becomes like such a map, a surjective map. Now we can get any probability distribution from sort of n tuples of possibly masked logits. And if you think about the equivalence relation of this surjection, it's sort of if I add the same number to all of the logits, then I get the same answer. So kind of this is curious observation number one, which is that this is actually the standard cylinder over tropical projective space. So projective space, you define punctured n space modulo multiplication by non-zero. And that's exactly what we're doing. It's just that the multiplication is tropical multiplication. So there are actually a lot of papers. I've never seen this observation, but there's a lot of papers with various observations about the relationship between neural networks in the tropicals, language models in the tropicals, language itself in the tropicals. So there's a lot to say here potentially. And I wanted to observe that as a curiosity. And then the second curiosity here is that softmax is actually the sort of unique entropy maximizer. And I think this is the correct statement. Oh, sorry, I should say fix some L and R. So given a constraint on sort of the total energy, then there is some beta so that softmax maximizes the entropy with that constraint. So this is a really interesting way that softmax pops out of something relatively simple. But why is this interesting? So this interested us because of this result. I don't know exactly who to credit this observation to. I kind of inferred it from like John Baez's blog posts and Tom Leinster's talk. But basically, the chain rule for conditional entropy is one cocycle condition for an operad. And the reason that interested us is that we actually wrote a paper about cocycles in 2023, where we kind of found that, inspired by a cohomological viewpoint of elementary school arithmetic, we found that carries in a general setting, sort of a dynamical system setting, could be identified, sort of carries with a nice asynchrony property, could be identified with one cocycles. And basically, there's a left-right issue where you have to reverse the order. So if I have an action on something, then the carry should be a one cocycle for the opposite monoid. So it may be that somehow entropy has an interpretation as a kind of carry for the opposite of the simplicial operad. So if I split a state along a probability distribution, maybe there's a sense in which this produces a kind of extra quantity, which is the entropy. And my basic question to end here, shockingly close to the right amount of time, is to say that like our single most textbook example of doing this form of selection is maximizing a one cocycle for an operad. So my question for all of you is, can you please tell me why we're doing this? Why is this a good thing to do? That's all that I've got at the moment. Thank you very much for hearing me.
Thanks a lot, Andrew. And indeed, there was a lot there. So thanks for sharing that. So we are right at the hour. So I think I'm going to go ahead and stop the YouTube live stream now. And if you're available to stick around for a little longer, Andrew, and answer any questions.